Swayam Prabha. Digital India. Educated India.
Morning. Let's start again. So yesterday's was okay, everything? Did you learn something? Kind of overview and overall idea about different things? So today we'll continue in the same way into some of the other areas. And again, the idea is the same. Like it's not to learn into details, but just probably if you get an overview, so you know that this is some of the important issues. And so that's the idea behind it. So we cover two things today. One is this metal release, and because the recent times, the use of metals and alloys in external products are increasing, right? If you look many years back, if you see the buildings, you don't see so much metal items exposed to outside. Maybe you may see in the brass things like as a part of the statue and things like that in India. Similarly, copper roofing in West, but not like so much other materials are used. But today it's not like that. Today there is so much metallic components are used in the building outside, aluminium, and in a normal building, I'm saying steel is used so much or different types, and there are buildings with constructed totally using aluminium and totally using titanium and things like that. So since there is a bigger area of the metal and alloys that is exposed to outside conditions, and there are a little bit more thinking about what is released from metals into the environment and how that will cause a problem. It can be poisonous. Some of the metal that is released, some of the metal that is released can create problem for microorganisms. And if it creates problem for microorganism, means indirectly it will also affect us. So this is a thinking that way it is people want to control this release. And of course there are a few other things as well I will discuss here that is all to do with metal release also in the biological systems like that, a little bit an overview, because there are more and more materials also used in contact with biological systems, and there also you have the metal release problem. So that's what we are just going to look at a little bit. So mainly the source of the metal is coming from the this architecture that is from the buildings, but it can also be coming from other things as well, this mining, industrial sector, agriculture, and that also can release if the metal related things are used, that also can release metallic ions, and that comes to the earth and also to the water, and that way it is a problem. But we are more worried about the buildings, because that is in most of the cases the metal that is released from the building is due to corrosion problem. That's what we are looking at. It's a corrosion problem that is causing the metal to release, and that's more interesting for us. And so that's what we will look at a little bit more into detail. So as I mentioned, that the amount of material that is used in the building construction is increasing the metallic materials. You can see that if you take the steel, about 43% of the steel is used in construction sector, and you can also see that there are many other things here which is the steel is used. And again, if you take some of these products, and this is also getting exposed to the environment, and that way metal release is possible from these applications as well. Although we are taking the building application as the main thing that is releasing the metal ions into the earth. Copper, you can see that the main application of copper is the building constructions. And if you take it's basically this particular statistics from the United States. Maybe there is more copper use in the West, probably compared to India. And many times, sometimes you will see that the tubing, which is for the water piping systems, and all those things in the West is made by copper. So there is, and roofing as well. So there are more use of copper in the West, and that's probably the reason that you see here that there is a lot of copper is used. Similarly, aluminium consumption, if you take, that is, this is the part which is coming from the construction. Although you see here that amount of aluminium used is a little bit lower compared to that of, if you take this yellow color one, that is transportation. Transportation sector is the one which is dominated for the aluminium because of the lightweight, but aluminium is also used to a large percentage in the construction as well. And this is increasing this aluminium involvement in the construction, because again it is coming with the lightweight because of that. Because you think that the lightweight is not important for a static applications like construction. That's not the case, because now we are making a very tall buildings, complicated buildings, and if you want to make the metallic component related to that building, you need to use a cranes. And so the crane is costly to use, and that means that if you are using aluminium, an aluminium component probably will weigh only 1/3 of the steel, so you don't have to have the heavy cranes and other machineries to use the installations. So the installation cost, if you are making a building with aluminium, is very much less compared to that of if you are making a building with the steel. So again, that's the reason that aluminium is entering into more and more construction, especially offshore constructions. Like earlier, you can see that in the oil platform in the offshore, mainly steel material is used for the accommodation modules and things like that. But now everything is changing into aluminium basically because of this reason. It can be easily transported, and that way the cost will be less. So just to give an example of, I just take different examples of this metal release. That's what I want to show you, just to give a glimpse of it. And so this is one of the studies which people have done, and metal release from the sources due to this acid rain and corrosion. And this is a investigation, it's quite nice investigation from China, which is this Guangzhou. This is a city which is a southern China, where there is a lot of urbanization, industrialization, and so there is the air is polluted, and air is polluted, and that means that the rainwater, basically that's a quite problem, right? If the air is polluted, the rainwater collects this pollution like SO2 and noise gases and things like that in the air, and it changes into acid. Like if water reacts with SO2, you produce an acid species, and similarly if it reacts with the noise gases, also produce an acid species. So this is issues that way the pH will be less at the end. So here I took this from this paper, actually looking at the dissolution of the zinc, copper, lead and cadmium, for example, and you can see that there is a quite significant amount of this material is released in different sites. If you look at here, we'll look at that in detail, but before that, you can see here that the allowed copper level is approximately, and little bit difficult because it depends on which standard you look at it and things like that, but at least we can take it as approximately allowed copper level is around 30 ppm per kg of soil. If you take like that, 30 ppm. Allowed zinc level is around 10 ppm, lead is around 80 ppm, and cadmium is around 5 ppm. So this is a kind of levels which you can allow in the earth, but you can see that the amount of metal released here is significantly higher than that. If you look at zinc, if you look at copper, many places it is more than that, or lead or cadmium, it is much higher than that. If you look at here, you can also see that this S1 here is coming from the commercial sites, S2 and H6, S2 site and H6 is coming from the road side, and S3 and S4 is the public building areas, that is S3 and S4, and this S5 and S7 is from the industrial sites, that is S5 and S7. And can you see a pattern here? This S5, you can see that the amount of release is much higher in the industrial area, and maybe there is much more pollution there, and that might be the reason for this much higher release of this species around that area compared to the other area. And this S sign is from a public park, for example, and you can see that it is a little bit lower there, and there are a few other things, that is organic matter and things like, which is not relevant for us. I removed that. So that's the reason that this OM and things like that, what you see. So you can clearly see a pattern here, depending on the type of place and exposure, where you expect higher pollution for the industrial sites, you get a much higher degree of this release compared to that of other region. So this is a side that people are worried about, and this needs to be controlled, and that's the kind of action which you need to take. And I don't know what extent you have this thing in India, but at least in the West, it is very seriously taken, and that means that there are strict rules for using metal items for the building constructions, and even one of the university which will come later, and they did a lot of work in this area. They started giving consultation, so that anybody making the building, they consult them and they can suggest better materials and things like that to reduce this problem. If you look at the global acid rain, this one, and one of the interesting things what you see is that, like we expect that we use in India, we use a lot of fossil fuels, right? And a lot of wood is burned and things like that. There are industries with probably less, more polluting, like less restriction on the pollution and things like that. We expect more acid rain in India, right? But if you look at this graph, you don't see that. Of course, this may be a little bit old graph, so there may be slight changes, but you don't see that here. You can see that Europe is one of the places you see a lot of acid rain, and you see also in North America and part of maybe North America and South America as well, and that's recent region that you see a lot of acid rain. So that goes back to the history. So that means that the acid rain what you see now is not totally to do with yesterday's pollution. It is coming from the historically for over a long period of time. So where the Industrial Revolution started, it is Europe. So Industrial Revolution started in Europe. So many industries have come up, and there is a lot of pollution has been already done at that time because the restrictions were much less at that time. So that makes much more acid rain. So now you can see that why Europe is more worried about it. And so there is more acid rain chances in Europe. It is coming down probably now, because now over the last many years, the restrictions has been, where there's much more restrictions, and that way the pollution is less, probably the degree of this is coming down. But you can see that in general, there is more pollution, acid rain chances in Europe. So KTH has done a lot of study from the corrosion point of view and with the electrochemical point of view. KTH is the Royal Institute of Technology in Stockholm. KTH in Swedish stand a different name, that's why it's called KTH, but it is like my university, like DTU or IIT. They also have only technology, engineering, science and management. They don't have other things much. So it's the similar type of university, and they have done a lot of work in this area in the Europe, understanding that what kind of metals can release from the buildings and what it cause problems and things like that. So that's what is written here so I took some slides from them. That is, generally increased environmental concern relates to diffuse dispersion of chemicals, including metals from the outdoor applications. So this was the kind of case which has come up in the Europe within the 80s and 90s. And they did a lot of work in this area, and looking into what could come out from different buildings and things like that. So one of the major thing they did is the release of copper, because there is a lot of copper roofing buildings in Europe, and it is totally covered with patina. So that means that the corrosion rate of the copper will be lower with the patina, but the problem is that this patina itself is soluble in the lower pH conditions. So that's the issue. So it's not that copper is corroding more, because copper is not exposed. The patina is the one that is exposed to the outside condition, but patina itself is soluble if the pH is lower. So here you can see that, like so this is a experiment they did outside, for example, taking a copper sheet and exposing it from outside from around 800 days. It's about 2 years or more. And you can see that the copper oxidation rate comes down very, very fast. And very, very fast means it's not like within 1 hour or something like that. Within few days, the copper oxidation rate comes down. And that is because this patina is forming the amount of oxidized copper. Oxidized copper doesn't mean that's a patina, but at least the oxidized copper is forming, and that is increasing with the time. And this slowly changes into patina, and that's what happens, and that's what you see in all these places. if you take this copper roofing. And this is also what it says, that is improved corrosion resistance times, and that is what it says, that is over the week this copper dissolution rate is reduced because you have an increase in the corrosion, this patina formation and things like that. So that is naturally, that's what you see in the case of copper, because patina is forming, and that way this dissolution rate is decreased. And so one of the results which they have, and they did at different places for the studies related to this copper runoff from the patina. And what they found was that, you can see here, these are different cities and places in Europe. And you can see that if you take the marine sites, this one, and urban sites, and really what we expect, you can see here, the marine size is actually lower, right? The runoff rate is lower in the marine size, because usually we expect the other way. The marine size is having a lot of chloride conditions, and we expect that marine sites will give much more runoff. But here it is opposite. Actually, it is city areas which gives much more release. Again, it is coming back to the same thing, because city area is one that is more polluted with cars and things like that. And that way there is much more possibility of acid rain, and that way there is much more release in the cities compared to that of in the marine sites. So that's the importance of that this urban atmospheric conditions you can see here. And then they also found that the metal runoff highly dependent on the prevailing material exposure and environment pollution conditions. That means that dry wet period, that's important. There is a dry wet period, means you have a wet period and probably there is pollution and different things like aerosols and things like that that's deposited, and like that also contains salt. And then when there is a wet condition, and that increases this dissolution, all these gases and other species in the environment is important. Surface composition of the patina, that is depends on the metal, and the patina composition and porosity, age, and that's important, because if the patina is porous, not only the patina will dissolve, but also the environment will be attacking the copper. And that way, I'm taking as an example of copper, but it is the meaning is the same for all metals. And that way, again, it increase. Another thing is what they found was the inclination is very important. Inclination, orientation, size, geometry, and all these are also important thing, because it is runoff, right? So that means that it is runoff. This angle is important in this case. And if it's a horizontal case, there is less runoff compared to that of if it is in a 45-degree angle or something like that, the roof is sitting. So there are number of parameters determining this. It's not just a simple thing. There is number of parameters determining this. And at the end, also the rainfall quantity and intensity, this chemistry of the rainfall, and that is basically this acid rain, pH and things like that, and time of wetness. Time of wetness is that it's not necessary that all the time you have rain. You have rain, intermittent rain, but in between you have this time of wetness. Time of wetness is like condensation and things like that. Morning time you have cold weather, and that way you have condensation on the surface, and the condensation is slowly, making the things to dissolve. It may not be coming out, it may not be flowing away, but then when the rainwater comes, it is flowing away and things like that. So there are many factors that it determines this flow, and that way this contamination. So they actually come up with an equation. It's not a perfect equation, and that way you can calculate the copper release if you know many of these factors. For example, that is coming from their work and collecting a lot of data from Europe at different places. If you look at here, that you can see the copper release rate per meter square per year of the roofing is equal to, you can see that it's a function of the SO2 content in the atmosphere and rain. And rain is concerned, the pH is the most important thing. So there is a 10 to the power of this pH with this one, and also this cos theta divided by cos 45, that is the angle of exposure is as well. So you don't see so much the other species in this, and that doesn't mean that other species are not having any effect, because in their studies, in their experiment, they didn't find. So it's an empirical equation which they come up with from their experiments. So there they found much more influence of the SO2 rather than the other things, and that way they came up with this equation. You can also see here in this map in the 2000, if you take different regions, how the metal release, right? For example, the red color areas, if you take, that's the most one. This is, let me see. Yeah, this is Norway. So this is Sweden here, and this is Norway. And this end of this Norway part is more release is there, and probably because of this is seaside here. One is probably seaside, and it also may be probably, there may be another reason for this, probably some anthropological reason as well. There is maybe more SO2 in the air or something like that. And so you can see here, the Denmark is here. This part is Denmark, and this is Germany. You can see that this is this must be Poland, and you can see there is a lot of emission release in the Poland area. Release also here in this part. This is Italy, and there also this German-Italy border, there is a lot of release and things like that. There may be a specific reason for that. If you go there and analyze, exactly if you look at their papers, you will be able to see that exactly why this is more in this region and things like that. There may be more industrial sites and all possibilities. So this is going on. There is a lot of work they have done after this as well, and there is a lot of understanding also in Europe because of this. And these days also it is going on. There are many cities in Europe, they placed sensors, and they could analyze what is the SO2 content in the air, H2S content in the air, NOx gases, so that all this information they can put into this, and that way they can find out that what could be the metal release. Because now they have a model, and this model can be used for predicting if they know the pollution in the different cities. So that's why they put these sensors at the different cities and collect a lot of data. Now they also started giving the advice. That means that this is what a construction project where our knowledge and research findings have been implemented by a discussion with material producers, urban construction officers, and environment management and property developers. And so they use alternate alloys because, you know, one is the designer want to get some kind of appearance for the outside. And so this is a kind of a trade-off with what material can be used, how we can control the release. And at the same time, they want to get a targeted appearance. And so, for example, in this particular case, they use, probably they had the idea of using copper. Instead of they started using the copper, aluminum, tin, and zinc alloy. And that way, this copper release is reduced by 40%, for example. So that's an idea about that's like if they want to, somebody wants to construct a building and they want to use a metallic material to get some kind of aesthetics and how you can reduce it. And this also come up with a lot of opportunities as well, because this alloy probably was not existing actually. Those alloys probably developed as a part of this, and that also bring a lot of opportunities for making new alloys as well with lower corrosion, like that. So that gives you an idea about a little bit on what is how important it is and what people do to understand this. They also studied the zinc runoff from the material, and so you can see here that is so here they plotted the rate versus exposure period for the zinc, and they did for about a year, 350 days. And you can see that there is two data here. One is the corrosion data for the zinc, another one is runoff data. Why these two, the two of them they provided is that, as you can see from this picture, there is, because of the environment go through the patina, and there is a zinc corrosion that is occurring underneath here. And you can also see that there is a zinc runoff, that is what is happening on the top. And so this zinc runoff, which is coming from the patina, which is dissolved in the acid rain and things like that, and that is what is shown here, for example. And this shows the corrosion rate of the zinc. And what you see here is that if you just take these two together, the sink corrosion rate is higher initially, and compared to the runoff rate, because the patina is quite small. But you can see that with time, the sink corrosion rate and the patina dissolution rate is almost becoming same, and which means that's kind of reaching a steady state condition. Whatever patina is forming, and that patina is dissolved as well. And a nice situation would be that is the corrosion rate is, this patina dissolution rate is lower than the corrosion rate, for example. So here it is equal almost at the end, and that is reaching a kind of a steady state condition in this case. Actually, I had a graph, probably I forgot to put that here. There is another graph I had. That graph is showing that, yeah, I had another graph. That graph is showing that the copper release rate, they studied from 1990 almost now in the Stockholm area, and they see that the copper runoff rate is decreased now. So which means that more awareness and more nice vehicles now, better cars and things like that, the pollution is less, and because that this issue is less now, and that way the copper runoff rate has come down in Stockholm. So, but this is a kind of target. Also, what they have, they want to reduce this. So this is just from the same thing, that is just they also propose the mechanism of this copper runoff. So you have the copper and not copper sink, and I think this is nothing complicated here. And sink get converted to zinc hydroxide first, and that is because they analyze the layer formation with time. Zinc hydroxide and zinc hydroxide get converted to zinc carbonate and hydroxide because there is carbon dioxide in the air. And then they also found this kind of compounds with this chloride in it, and hydroxy chloride type of compound with zinc chloride, and this must be much more soluble in the water compared to that of this one because of the chloride. And then it forms a sodium salt of this, and then it is dissolving into the water. So that's a kind of sequence of product formation from the zinc hydroxide to zinc carbonate, hydroxy chloride, and then you form the sodium salt, and then it is dissolved into the solution. That's what also you see here with in interaction with the atmospheric conditions, where you have oxygen, H2O, NaCl, SO2, and CO2, and all those things. Yeah, this is also from the same studies, actually zinc corrosion and corrosion classes under different environments. For example, zinc corrosion attack in micrometer scale, it is shown here. And so they looked at, depending on where this zinc is placed, different corrosion category. So you can see the 0.01, that is office, schools, and museum, where is the internal. And coming from that to the CS condition, that's the extreme condition, there is about 8.4 to 25 micrometer level of corrosion when you have these very high chloride conditions and things like that. Again, they made an empirical equation for this corrosion rate for the zinc, and that's what with the SO2. Again, the rain with H plus concentration, and in this case, nitric acid is also so important in the air, and they made an equation like this, empirical equation. Again, this is coming from the experiments, the data, a lot of studies from that. You must have heard this name. Probably the Christopher Lee Graf. Christopher Lee Graf is a professor in Royal Institute of Technology, KTH. He did a lot of work on atmospheric corrosion, and he has also written a book on atmospheric corrosion. So here you can see that there is another study where they took the bronze, quaternary bronze, and tried to see that in the artificial rainwater, and they made the artificial rain with this kind of composition, which is maybe based on the analysis of the actual acid rain. They collected and identified what are the major species in it, and that is what is this one. So if you look at, of course, the pH, chloride is there always in the acid rain. Nitrate will be there coming from the different pollution. SO4 is, it's also possible that SO2 is oxidized into SO4, or it's also possible that many other sources, and all these organic species from the living organisms that's coming, and so that's the way that all these species are. And then they did the acid rain, and then they found that what is more dissolved from the quaternary bronze. And again, you can see the copper is the main. So this is for 48 hours, and this is for 30 days. You can see the copper is one of the major species that is dissolved from the quaternary bronze. I don't know do you know, Lakshman, the composition of HSAR composition of quaternary bonds? It's a tin, copper. There is also tin, copper, and zinc alloys, but there it is. It's not shown tin. It is zinc. It is shown, and lead is shown. But normally it is tin. Tin is there in the bronze. Yeah. But here it is shown actually copper and zinc is dissolved and lead is dissolved. That's what is shown. But copper is the one which is released more. This is another study which is coming from Germany, which they have done. There are, as I mentioned, that there is a lot of this copper tubing is used for the water supply and things like that in Europe. So they are also looking into that in the family buildings and things like that. When they have the copper, what is the kind of release of copper and different materials also into the water? So this is another possibility, that is when you use the tubing systems with the copper and the metal is dissolving into that and contaminating the water, for example. So as I mentioned, that is also important is a metal release into the biological systems. So people also started looking into metal release into the biological systems. So stainless steel is widely used for biological applications, and there can be many things can be released into the biological media as well. And the food industry is another thing where stainless steel is used so much, and the food contamination is another issue, and there is a very strict regulation on it. And for example, this particular study has done with taking different biological fluid and try to understand the release of these elements from the stainless steel in different solutions, for example. The interesting thing for us is that you can see that iron is dissolved more in all these cases. That's understandable because these are iron-based alloys. And you can see that little bit of chromium is also dissolved in all these cases. You can see this gray color part. Chromium is also dissolved. More interesting is the nickel release. For example, if nickel is released, nickel is very allergic material, and many people get metal contact, metal related allergy, and nickel is one of the really allergic materials. So that's very, very important. Most of the time when they use the stainless steel as an implant in the body, people get allergy. That's because of this nickel release. So you can see that some of the solutions there is in higher nickel release. We don't go into that detail, but we can look at probably specifically to the chemistry of that solution like that. But there is nickel release. Almost all over there is a nickel release. And that's a worrying thing actually, because nickel release causes problem biologically, because it causes a lot of allergy. So there is a study which we did in it's not me, but there is one of my colleagues did in Denmark actually, and then that was published together with one of the hospital in Denmark. That is, I don't know whether any of you have had this problem. If you take the old Apple computers, and when you use old Apple computers, when you and you touch, and then you start getting the allergy, you get a reddish color and itching, and you start getting the allergy. Not the new ones, but the old Apple computers. And the reason for that one was, do you know how this Apple computer, this frame is made, which I was telling yesterday? It's aluminum, right? And aluminum, and it is anodized. After the anodizing, they do a process. What is that? During the anodizing process, you form a porous outside layer. That's the way the anodized layer is formed. After that, they do a sealing process in order to close the pores, right? So the anodization is like that, anodizing, and then a sealing process in order to close the pores. The people can do the different types of sealing process. You can do the cold water sealing, hot water sealing, and people also started using nickel sealing. And nickel sealing will give a little bit more corrosion protection compared to the normal sealing. So Apple computers, they used nickel sealing process, they didn't think about these allergy issues. And at that time, or whoever bought Apple computers, and many of them, when they use it, and they had these allergy issues. And it was a big problem for Apple to solve that, because in the West, it's a big issue. That is, they can go to the court and say that they need the compensation. And so it was a big issue for Apple to solve. And so you can see that this is a kind of allergy. And there is also another thing, I don't know the reason, and there's nobody, I think, in the medical world also know the SR reason for that. In the West, the metal contact allergy is more in the West compared to that of in Asia. Maybe because of the, the difference in the skin and things like that, and probably it's basically because we have maybe more, melanin, or I don't know the reasons for that, but whatever it is, I think this allergy issue is much more in the West. And that way there are more people got affected there. And now, of course, they removed the nickel, and now they don't use the nickel sealing. And that's what is shown here as well. That is, if you take the artificial set and from different types of stainless steel, how much nickel is released. So this is allowed nickel release rate, and how much nickel is released from the different things. And that's what is shown here in this case from the stainless steel. So it can go beyond the actual, even from the stainless steel, you can have beyond the value of that is allowed. And yeah, so now they stopped using this nickel sealing process for the Apple computer. So you don't have any problem now. And they changed the process. So that's an example of how problematic it can be. And so this is another thing which is showing that the metal release from the biomedical cobalt chromium molybdenum system. And again, I think the interesting part is the chromium release here, because chromium is one of the metal you don't want so much. And so you can see that with exposure time in this biological media, the chromium release is increasing. And if you look at here, it's almost goes from probably 3 or 4 times with exposure time. So the chromium is released in this, but I don't have a data here exactly that how much chromium is allowed in the body, but that's a good thing to look at it, that how much chromium is allowed, but I don't have the data here. But you can see that it is released from this cobalt chromium molybdenum alloy. And the important thing here is that compared to the stainless steel, the amount of chromium is also high in this alloy compared to the stainless steel. So that also increases the chance for more chromium to come out. And this is a similar study, but it is again showing that how much this chromium and different elements have released, like from difference. I think more like a summary of this one with this graph, which is showing like different amounts like cobalt and chromium, how much it is released. I think that's more or less I have in this area. That is just to give you a glimpse of that is like this is an issue, and this is an issue, and people are looking at from the corrosion point of view, and in relation to the biological system, the medical implants, in relation to the building constructions and things like that, and it's an important things to look at it, and people are looking at it, and people are also trying to find solutions for it as well. I think there is a lot of opportunities for this to be done in India, and especially in relation to the, I think you are also doing a little bit now, right, with these statues and things like that, right? So, but there's a lot of scope, because I don't think that this research is there that much in India. So it's also to initiate something like that, right? They have done? Okay. It is. Temperature will increase the, definitely it will increase the release rate. And I don't know whether there is a temperature in the equation there. Yes, there is a temperature in this part of this equation here. Functional temperature. It's part of the equation. I don't know whether the other equation has a temperature in it. This equation doesn't have a temperature in it. I don't know why. But temperature is definitely will increase the metal release rate. Yeah. As like corrosion is increased with the temperature. It's a kinetics is accelerated to increase the stability of the pattern. That's more or less they do it in the. I think that's may not be in this case, but indirectly I can tell this as another way. That is, for example, of course, here I don't think there is a patina formation here, but indirectly we can say that that's what that they have done here. That is by alloying like this, and they reduce the release of copper. It's not patina, but it is like the reduced release of copper. I don't think that you can do much with the patina composition itself, because that is formed because of the environment. The only things what you can do is that you can make the environment clean. And so that's all. And that's what also you see that, as I told you that I forgot to put that slide, but there is another slide which is showing that how the metal release rate has changed over a period of time in Stockholm. And which means that the environment became more and more clean, and that way there is a reduction in the release. Otherwise, what will happen is you need to attack with the alloy, and you can use a better alloy. That means that the dissolution rate can be reduced. I think that's the approach more. Not stabilizing the patina, because patina is a compound that is formed over the years. It is impossible for you to do anything with that. Yes, maybe you can think in another way. That is, you are going and spraying something onto this patina structure, and how feasible it is, I don't know. You understand my point. That is, every green color building, you go and spray something that will stabilize the patina, and so that it can be reduced. But I don't know, if you look at from the different point of view, commercial point of view, and a practicality, how workable it is, I don't know. But it might be possible. That is to find some chemistries, or find some, even you can find some polymer compound, right, which can be sprayed, and that will keep the patina and things like that. So that might be possible. So it's yeah. I don't think, as far as I know, I don't think that anybody is trying that. I think everything is going towards reducing the pollution, because this is anyway the drive. You will see that in my next presentation, there is when they are trying to remove the carbon dioxide and things like that from the atmosphere. So that's the way the things are going.
Again, it is becoming a question after 10 years or later.
Yeah.
So how to ensure a technology remains always a solution, not a question?
That means that what you want to know is that if you are having some technology,
yes,
and whether that technology will be perfect, good after 10 years,
yes,
like that, right? It's difficult to say. And only thing is that, of course, when we are looking into with today's knowledge, we are looking into whatever is, because we have, if you take the last 20 years back, compared to that, we have a lot of new knowledge today. And with that, we have much more understanding on what metal is better and what metal is not good, and what is bad for the environment and things like that. And that way we take the decision, and that way we make the new technologies. But doesn't mean that these new technologies will not have any kind of issues. We will dictate that after 10 years. The only things what we can ensure is that those problems coming from this technology will be much less compared to that of what we built 20 years back. That's all we can ensure. And there is nothing guarantee that it will not, it will be perfect. For example, they built this with this alloy, and of course the copper dissolution is reduced. Probably you will see that there are some other things are coming out of that, and probably that is affecting in another way. It's wild thinking, but similar to that other technology as well. So nobody can ensure completely that when you have developing a technology, it will save after 10 years. With our knowledge, we can say that it is better than 20 years or 30 years back.